recording. We'll share our screen here. Guess what we're going to talk about today? Ta-da! Inductors, yay! Excuse me. So, yeah, big surprise, chapter 20. But here we go into inductive circuits. So now we're looking at actual response and stuff of inductors. Let's see some of the characteristics. Let's see, we're going to mix just like we did with capacitors. You try to examine the inductor alone and look at the characteristics of it. Now we look at it with, as you can see here by the second topic, is we're going to look at inductive reactance and resistors in series, and then look at the impedance triangle here and look at it in parallel. So he goes a little quicker in this chapter than he did with capacitors. Well, mainly, I mean, now we're getting into these concepts and in a way, the similarities and whatnot. So hopefully we have a little easier time grasping the math with this. Um, let's see, and we'll look at the actual charge properties of a coil, and then again, audio frequencies and radio frequency chokes. And then, that's communications and media. It used to be just, radio, but these days we'll classify pretty much anything that's like that deals with this under media. And then, a little synopsis of inductive voltage, if you will. But yeah, let's go and jump in. Let's just jump in. So, I mean, the good thing about tomorrow being off, we'll kind of catch up with the textbook with labs and whatnot. Um, I mean, I'm glad we did do the lab we did on Thursday. It showed us at least the lag portion of excuse me, of inductors. So what's unique about inductors? So this is a big one right here, right? That the sine wave of current here, see that the IL lags the VL by 90 degrees. So if we look, we got an example here in A, right, with just an energy source and just a straight inductor. So we develop our voltage here and we look at it. Now recall that in the lab, what's the problem with just using a straight inductor is how very little voltage we're able to develop across the inductor, and that using the resistor actually sets us up for a much more stable circuit. But in any case, this just looks at it in a purely theoretical view, like this is the property of it, right? So yeah, when the sine wave variations of the current produce an induced voltage, then and that's just so we're looking at just remember just purely inductive circuit, right? So it'll be exactly 90 degrees as we see here in figure 21. Um, the lab we had didn't give a straight example of this because we did have the resistor in there, so we didn't get a pure 90 degrees. But we did get to see that the shift happens in the opposite direction of the capacitor, right? And the thing to remember about inductors versus capacitors, now this is so we consider that a positive 90 degrees. So notice in C here, figure C, that our phasor diagram is in the positive direction. So that gives us a little thing where they have a little meme or what do you call it? Like a little mnemonic, that's what I'm looking for. Where they say it's Eli the Iceman. And then what this is supposed to help you remember is the properties of inductors and capacitors. So with Eli, E-L-I, right, the L in the middle represents inductors. And what's that saying? It basically says that the voltage is ahead of the current. Okay. So by how much? By 90 degrees. And then ice ice with the C in the middle. That's C is for capacitors, and that current is leading voltage. And so again, by the 90 degrees. So it's just a little, I had mentioned that, I think I have, but yeah, Eli the Iceman. It's a little thing to help remember. I think just about every technician out there knows that one. Really, it's a funny little one. But anyway, but yeah, this is the classic case. Purely inductive circuit to show us exactly how we're. And I mean, if you look at the amplitude, yeah, remember the little red one, that is current. So generally, the current amplitude is never quite as high as the voltage amplitude. So, and that's what we're looking at here. Okay. So now we go in and look at the properties of a purely inductive circuit like that. So the phase angle is 90 degrees because the voltage depends upon the rate of the change of the current. Okay. And it's an interesting thing about an inductor because of the coil like that. So you can see in the reverse mode that if we look at the crossover points, right, and when they match up, so when this one's high, this will be at 0, and when this one's at high, the other one will be at 0. As far as examining the sine wave, peaks and lows. And the current wave doesn't have its positive peak until 90 degrees after the voltage wave. So pretty much a reverse um, reaction that we're experiencing here is compared to like a capacitor. So because of the way that this is occurring, then we can make the statement that the current is lagging the voltage by 90 degrees. And again, remember, even though we have this lagging phenomenon occurring, that the frequency has not changed. The frequency of both waveforms are still the same. If we're putting in 60 hertz after the inductor, it'll still be 60 hertz, just that the one waveform is now lagging by that 90 degrees as opposed to prior that it went into that. Okay. Okay. So when we look at the coil and we have series resistance to it, okay, then the current is limited, let's see here, by both the inductive reactance and the resistance. So if you recall from the lab, okay, remember you measured the actual resistance of the coil. And although that resistance is extremely low, that's considered your DC resistance of that. And then we excite it when we put the sine wave to it, and that's when we induce the reactance. So then we have the reactance factor in there as well, but something to keep in mind that we will always have that little bit of DC resistance. And remember on the one, I mean, they were small, like the one I think was around 2 ohms, the smaller one, and then the bigger one was like about 24 ohms, but excuse me. But in comparison to a typical resistor that you would have in the circuit, that would be considered really small. But always remember that it is there. It's not something that, like if you were to build a sensitive circuit, especially like in communications or something like that, where you do rely on good response, then that resistance factor will come into play. So just something there, again, we're examining, the unique properties of these things, something to keep in mind, especially when you go through the homework. But so this current is the same in the inductive reactance and in the resistance, since they are straight in series, right? And that was something that was interesting. That's why I actually like putting that lab out to you guys last Thursday. So we actually got to see how this works. So yes, remember, so since they are in series, and if we have the resistor in there, we basically are developing that voltage across the resistor and forcing that current to go through that inductor the way we want it to. So you could say that the resistor in series with the inductor like that is actually a much more stable circuit than just the inductor alone. So, but because of that property, they still would have their own series voltage drops, right? So we would develop the current. The current would be the same on both, just like we're used to doing, and then we would develop the voltage across both. And then remember, if we had the resistor in series with the inductor, there's still we're still going to have to do our phasor diagram and then develop our little equation for that. So, but yeah, that's something to keep in mind. And if we were to actually do like a purely examinative circuit, then we would have to take into account that we would have, see, we would have to, each has its own series voltage drop, and then that would be equal for IR and IXL for the reactance. So these would be, both parts of the phasor diagram, one point being on the 0 line and this one going off on the 90-degree line. So, and here's a type of phenomenon we would expect to see. And there's our phasor diagram. You see it with voltage responses. So we have the resistive voltage going along here, and then we have the inductive voltage going up at 90 degrees here. Okay. So if we take a look at the circuit, and it's a straight series, right? So we know that if we do when we do develop the current, this would be the current total for the circuit, and the unique things would be the voltage. We would have unique voltage drops across both of our components here. And so that's essentially what we're looking at. So if we take a look, we see the current curve is the very top one. Okay, and it'll have a nice shallow because current amplitudes are lower. And then we got the next one is the voltage across the resistor, and we have the voltage across the inductor. And then, of course, the very bottom one is what we're feeding into it. And that basically shows you your responses. So here's our resistor, right? So notice no phase change to it, but here's the inductor, and yep, we definitely go right out of phase, and we see our crossover points there. So when this goes high, he's at a 0. When he's at a 0, he's at a high. So we see our crossover matchup points like that. Okay. So now we examine the phasor diagrams, if you will. So same deal. We're still using Pythagorean theorem. Okay. So yeah, and it's much easier using the phasors. I mean, basically when we go and see these circuits, immediate thing is realize what values you're going to need, draw out your phasors, and that way it'll help you draw out your equation. So if I were to draw out this point, I'd have, okay, my resistive voltage response, and then I have my inductive voltage response. And then I would just go ahead and what's my voltage total? Well, we would just plug in the equation, Pythagorean theorem again, and develop what our voltage amplitude would be. Will you get out of here? Get. Oh. Ooh. No, dog. Hold on. Get. But so, I mean, this is like now we're basically reusing the same tools that we used before. But the thing to remember again, that we are in the positive 90. So if we were to develop this all the way and find out what our actual angle is overall response, we would have to take that into account, right? And that's where we go here. So we draw a triangle out with our points, and then we go through, plug in Pythagorean theorem, find out our amplitudes. So we take a look at, and we do it with the voltage because series circuit. So the voltages are our changes. So we have resistive voltage and inductive voltage. And then we take a look at the impedance. And again, the same deal, right? So resistive element, inductive element. And then we go ahead and develop our Pythagorean theorem and come out with our overall magnitude for that. Okay, again, positive 90 direction. Excuse me. And then we go into the fun part, okay? So, and these are on your formula sheet as well. So if we were to take a look, we would have like this, the inductive series circuit, and we would have our formulas, what we're looking for, what phasor diagrams we want to go ahead and use. So we should be used to seeing this little fun one down here where what theta, the angle of theta is equal to arc tangent of the inductive reactance over the resistor. So we plug that in, we know we get our values. So in this case, X of L is 40, the resistor is 30. Do the division there and then pop the arctangent button on your calculator. And then we see that this one is 53 degrees. So remember, anything over 45 degrees, all right, or under 45 degrees means it's either more inductive or more resistive. So in this particular circuit, since we're at 53 degrees, we're going to be a little more inductive in this circuit. But otherwise, it's pretty balanced. 53 is pretty even. And then we jump into the parallel element. So remember our changes, right? So in this case, our phasor diagrams are going to be a little different. One, we are going to want an impedance one. So the good thing to remember here is we're always going to want the impedance triangles. And then we have to just basically look at the circuit and think it's like series, parallel. What are my changes here? So in a series one, our voltages are different. So we develop a voltage phasor. And in the parallel, our currents are different, right? So we develop a current phasor. So let's take a look at it. So we have draw out our phasor diagram and we're looking for I total. So we develop the two different currents in this case. So what is our current for the resistor? What's our current for the inductor? And then go ahead and do our Pythagorean theorem and come out with our overall magnitude. Just follow these steps, boom, boom, boom. And just remember the unique properties of each circuit, series and parallel. What are my differences going to be? And then we find the angle. So he's taking a look and we go and plug it in. We used to have our inductive current over our resistive current. We do the arctangent function. And notice it's 3/4 in this case. And this is the tricky part with some of these. So some of them, you're going to have these positive angles, and some of them you're going to have these negative angles. And it just has to do with, that lead lag phenomenon that occurs from one to the other. But you would always have your formula sheets, but just in case you're glossing over or going fast or something like that, just remember to watch for the signs, because that would affect it if I said it was negative 37 degrees, but if I came out and said it was positive 37 degrees, that's a big swing, right? On the phasor diagram. So just remember that when you have to work these problems, doing the homeworks or quizzes or even practice problems, that watch for those signs on when we're plugging in these equations. All right. So yeah, he takes a look at a little more closely at the phasor current triangle in this case. And he makes a nice even one, of course, right? 10 amps on each side. So come out with 100 plus 100 and just do a square root of that. Square root of 2, 1.414. And then it's anyway, but so you can see in this one that the current would be actually pretty high, right? All right. So we take a look at R. Fun part is doing the as you've seen, we have two choices when dealing with parallel, how we're going to do our overall impedance. We either we have the Ohm's law one where we do the impedance equivalent, right? Or we can do the reciprocal method where we would multiply out the XL times R and then divide by the XL plus R. And so you do have two options here in this case. So you can always do the Ohm's law one, which, yeah, that would be, if you're able to get those, we have the values. This is a much easier little equation to plug in versus doing the reciprocal method. But both should give you pretty much the same answers. So again, our phasor diagram, right? We have a magnitude of 5 amps all together here. So that's our I total going in. And then we have the current and the two different legs. So having the total, we have the voltage total. So we can go ahead and just plug in Ohm's law and get our overall impedance magnitude. So something to look at when we're looking at parallel circuits with an inductor resistor. So the parallel branch circuits have individual values that are 90 degrees out of phase. And because of them parallel, that's an interesting thing that we get versus the series. So, yep, and then we go ahead and plug in our current values, get our overall magnitude, and that would be the main line or the I total or the feeder current, if you will. And then because of the phenomenon, we always look at it as a negative phase angle that's developed between the line current and the common parallel voltage. So we do get that lead lag phenomenon that's occurring here. So, but in this case, and remember from the formula for X of L, and that's where he goes into this bottom line here, looking at the inductive reactance versus the capacitive reactance formula, where we were dealing with a fraction. In this case, it's a direct ratio, so 2 pi FL. So when we look at that, we say less parallel inductive reactance allows more inductive current to make the circuit more inductive, which basically which way is our phasor angle going, right? What's the magnitude of it all together? So and we would have a larger negative phase angle for the current with respect to the voltage in this case. Anything over 45 degrees. So when it goes over to 45 degrees, and by how much, that's basically how we're able to tell how much more inductive it is. Fun, right? So Q. So remember Q. Q is what we use to express charge. So in this case, and you do have to look at the phenomena. I mean, you have to apply this basically to both capacitors and into inductors, and to see what is actually occurring overall. And I remember when we looked, basically we're dealing, I mean, this is a coil. There's always wire windings, values are always different depending, right? So that'll dictate how many wire windings we have. But basically the same phenomenon occurs. So the ability of the coil to produce self-induced voltage. Now, it's an interesting little factor here, but it's indicated by the X of L, by the overall reactance of the inductor. But because in the formula, it includes the factors of the frequency and the inductance, right? 2 pi FL, frequency and inductance. But the coil itself, now remember, this is something I said previously, remember when we measured, the wire itself does have what they call a DC resistance to it. And granted, it's small, but it is still there. And that's the phenomenon he's looking at now. So what we would do is we would compare our ratios. So you can kind of see in the very bottom here that our equation to see what our charge capacity is of the coil. We're looking at it with the inductive reactance divided by an RI, its internal resistance. So when you start seeing that, because we're dealing with AC signals, sinusoidals, the reason that they draw the little r like that as opposed to the big R is to denote that this is like a DC resistance, an internal resistance. So whenever you see that for different components, because there are other things out there you'll run into in the future, and they will display it just like this to show what the DC response is of the circuit. Will you get out of here, dog? Go on. Oh, pull out here. Go. You're being a pain in the butt. But that's just, I mean, we're not going to really work with this much, but it is something to remember that is there. That, and again, there's no such thing as an ideal component, right? And this is one of the drawbacks of the inductor, if you will, that it does have this internal resistance. But as long as you take it into account and adjust for it, and that's why they do this. This would be more of a dog of a design phenomenon, if you will, something that we would have to take into account when we pick certain values of inductors. But for us, overall, it wouldn't really bother us. But this diagram, so what they're showing in the block is basically what I just discussed, right? So we look at X sub L and R sub I. And we draw it internally because this is only one component. And so when we do see something like that, so if we were to look at like basically the manufacturer specification sheets of the particular part, this would be a diagram we would see on there because it is a factor to take into account. But that is what they do with it, and that is why they do with it. Okay, any questions on that? We really won't. This just because it's part of the book, it's something, one of the phenomena to observe and note, and it's like, interesting. But I promise you, after pretty much this, we probably will never really re-examine this particular one, if you will. I didn't say that out loud. Anyway. So, and again, now remember this section here primarily is for like communications applications, audio frequency and radio frequency chokes. Chokes. What's a choke? Well, this is actually, believe it or not, chokes are something that an electrician should know about. It is something that you will run into out there, and it may be something you have to adjust for at some point. I mean, you never know. These days and age, we're running media wires all over the place, right? We always want our info and everything from our machines and this and that. Everything's programmable. Everything communicates on networks and whatnot. And networks are basically a media communications thing. So it would be something to observe. And so basically, we can use a choke to get rid of unwanted signals. Let's say you had I don't know, you had a particular circuit, like in this case, in this example, okay? So what he's trying to say, or what he's trying to do here, so notice the bottom statement. The inductance here is used in the choke to prevent the AC signal from developing any appreciable output across R at the frequency of the source. So we take a look at this, all right? We have what? An inductor that has a reactance of 1,000 ohms. We have a resistor of 100 ohms, so it's a 10-to-1 ratio there with our little sinusoidal feeding into it. Now, we take a look at the voltage being developed here, and you notice the voltage, of course, has a 10, pretty much a 10-to-1 ratio, just like the components did. So we have 99.5 volts across the inductor here, but 9.9 across across the resistor. Let's go into this. So, oh, that was really all he mentioned, huh? Yeah. Yeah. Well, and again, this we won't really. I don't think we'll actually really be playing with this so much in lab or anything like that. It is just something to know. And this is actually a phenomenon that we will get into a little later on as well, just based on mixing the circuits and doing them. But chokes tie into getting us into filters. And basically, you're using it to like block unwanted signals or to develop a more stable circuit, if you will. So you would throw something like this into an overall much larger circuit, and you see where your output's being developed here, and that would give your signal a margin of stability where you wouldn't be getting like little noise spikes, if you will, and this would be a way to block those. Anyway. So here we go. The general case, this is pretty much the close of this too, by the way. The general case of inductive voltage. So these are just unique phenomena to observe what, like, okay, what happens here? So the voltage across any inductance in any circuit is always equal to this. And it's an Ohm's law variant, right? So we're looking at L, and then what he's multiplying it by, that's a derivative formula from calculus. So we're looking at the change of I and with respect to the change of time. Because when we examine AC signals, I mean, the signal does vary over time. Now, granted, we could be looking at a current curve, but it has changes over time. So that's what the expression basically states. And so what it would state is that it would cover all magnitudes of current and whatnot. And that's basically leads back to the formula that we do. But so to show the overall response, you would have to take the actual inductive value, if you will, and this would tell you what your circuit is capable of. So, but yeah, this formula will give you the instantaneous value of B based on where you were to pick. So if you picked here and the amplitude is so high, well, this would be that instantaneous value. And that's what he means by this. But yeah, it's produced by the change in the magnetic flux. Because we're dealing with a coil, we're always dealing with the flux. We don't usually observe the phenomenon, if you will, but it is occurring. And so whenever you do deal with inductors, always remember you do have a certain amount of magnetic flux that's going on there. And so if you were to have like another circuit nearby or something like that, and they both have that, the flux, the way, they can conflict with each other. So we do have to be careful of something like that. Anyway, and so what else to note? That the sine waveform of current, I, produces a cosine waveform for the induced voltage, right? So the current goes through the component and develops a voltage. However, the inductor is lazy, so takes us a little time before we get that phenomenon happening, right? And because he's lazy, we end up getting our current and our voltages are out of phase then. So the current comes through, and this component decides, well, yeah, and because of the charge phenomenon occurring here, we produce a lag effect, and that's what's happening with this. The good thing is it's very repeatable, and we can always rely on this property. I mean, we basically can make the statement, how much is this going to be? Well, it's going to be out of phase by 90 degrees on this pure element here. So that's a good thing. And then applying Ohm's law, we can always say that the inductive voltage can be calculated as current times reactance in a sine wave circuit. And it can be. So we can always say, well, this is this, and we know how to find our reactance. We can plug a formula in for that and develop what this is. So we're still, I mean, really, when you get down to it, I know we've got all this new stuff, but really, I mean, we're still dealing with very much Ohm's law. We're using it all the time with this. There are some unique properties we have to take into account here, but I mean, overall, it's repeatable. And I mean, the main difference here, the formulas are similar for capacitive to inductive reactance. Responses are similar. We just have a different direction, if you will, of what's occurring. And that's why I say Eli the Iceman. That'll be your mnemonic or your little rhyme. Let me stop sharing that. And that's pretty much the close of that chapter. So that one, and then the next chapter, of course, will be basically more like applications of these phenomena, if you will. So we'll be examining, the inductor with the resistors in series and parallel, and observing the different phenomena occurring there. And then after that, of course, we're going to tie everything all together, and then hopefully we'll start doing some more interesting labs. No, I shouldn't say it like that. A couple of them will be fun. Where we'll actually be able to see what do we do with these things, and well, we'll take a look at a couple of them and see some of the more popular circuits out there. Hopefully, we'll get to play with one and even possibly I got to check. I'm hoping that one of our more final labs will make like a little oscillator, if you will, and hook up a little speaker to it. It's going to be a fun day in lab. I think I'm going to bring my earplugs that day. But no, we'll be able to vary the frequency, you know, and make little. It'll be fun. But no, I mean we have to learn the unique properties of these components. So we'll be taking a look at those in lab. So on Thursday, we'll be playing around. Of course, and probably be doing, since he brought it up in this chapter, we'll be doing probably series and probably parallel circuits. But but yeah, we'll be looking at that. That won't be too bad, but yeah, we'll examine some of the properties of the parallel versus the series and see what's a little different as far as like what our responses are. All right. And that's about all I have today, gentlemen. I'm gonna post the homework for this, and I held off on that quiz thing. I think what we'll do is we'll probably have a combined quiz, but it'll be more weighted in the later chapter, if you will. Take a look at something real quick here. So we have 17 and 19. So yeah, I'll probably do a 17 and 19 quiz, but I'll be honest, it'll probably have more chapter 17 questions on it than anything, with a couple, maybe about like 20, 25 questions. I'll post that today, and then we'll be all caught up. And was everybody able to, did you guys try those practice problems by any chance? Oh, the silence. No. But, well, if you want, I mean, it's up to you guys. If you want to, I can pull out those practice problems I handed out. We can go over them. If you guys want to meet tomorrow, that is up to you. Or we can just say, you know, tomorrow's election day. But and then we'll meet back online here on Wednesday, and then meet on lab on Thursday. And that'll actually get us right nicely back on track. So that way, when we do Thursday's lab, we'll do the series in parallel. We should have at least some of the homeworks under our belt. So we'll hit that, and then we should be good. And then let's see. And then next week we'll start doing taking a look at combinational circuits and stuff, if you will. You guys are gonna hate me so much, but no, just remember we'll have our formula sheets, and we'll take this here. We'll take a look at these, little by little, and pull them apart, see how they work, and see what we need to know to do it. And like I say, some of this stuff he goes over it, and yeah, they're part of the homework problems and stuff like that, but we won't use certain of those phenomena, like the Q. The Q is something to observe, but anywho, but so anyway, but no, yeah, if you guys want to, and that's up to you. We can, if you want to meet tomorrow and go over those parallel circuit practice problems, I can do that. Take a half hour and go through them. I think I can angle my camera here and have a notepad out and kind of draw them and stuff. I don't have like a digital camera. I pretty much use this and my phone camera or what I have. but it's up to you guys if you want to do that. Otherwise,
I'd be down for that.
you'd be down for that?
Yeah.
All right. Well, then, all right. Yeah, let's do that. We'll
9 o'clock.
make it like 9 o'clock like today, and then just like I
Okay.
say, take a half hour and just go over it and, or any problems, we'll talk about those and tear it up a little bit, I guess. Woohoo! No. I did tell you I have no life, right?
Can you record the meeting just in case I can't make it tomorrow?
Yeah, you want it? Yeah. Oh, yeah. Excellent idea. Yeah, I can. We can record it, and that way we have the practice problems and whatnot on video. Sure, we can do that. And in
Okay.
fact, I mean, if you want to keep doing, if it's something that helps, I mean, it's a nice little tool. We'll do that. We can. I have no problem with that whatsoever, gentlemen. In fact, because yeah, moving forward, well, we're gonna have more practice. I hate to say it, we're gonna have more practice problems. No. I just think that the practice problems help, drive home like more using the formulas and stuff like that, and a real circuit kind of thing helps drive the points home. Like, what are the important things to learn here and stuff like that, I think. But if that's a helpful tool, yeah, because I mean, each sheet, we can go over. I mean, even if we go over all of them, it wouldn't even take probably but half hour, 40 minutes and something like that, and then we can, yeah, and you guys can discuss whatever points are stumping you and stuff like that, and hopefully we can come up with some good stuff. Okay, yeah, let's do that. 9 o'clock tomorrow, and we'll record it, and we'll do those 2 pages of the parallel practice problems. And I think I can, yeah, because I think I can swivel. Oh yeah, I'll come up with something. I'll play around with it a little today. We'll see. It's chilly, so I ain't going nowhere. Yeah, let's do. In fact, that is awesome. I like that. Let's do that. So 9 o'clock tomorrow, we'll record it and we'll go over practice problems and all that good stuff then. So bring your questions and anything else you might have, and we'll go over that tomorrow too. All right.
All right.
All right then. I'll see you guys in the morning tomorrow then.
See you, Tom.
Oh yeah, I have a question.
Ooh, boy, I
Is it
just caught that. Yes.
okay on Thursday if I bring in caramel candies? I have this grandmother relationship with someone. They love to make candy. They don't have enough people to give candy to. I got a
Wait, this is
bag.
homemade candy?
Yes.
Oh my God, Will, I hate you so much. Yeah. In fact, yeah, we'll make
She's-
it our secret. I don't think the
We have a quart bag full of them.
oh, crap. Are they individually wrapped or is it like some-
Yes.
Oh wow, it goes all out, huh?
Yes, she made like 8 bags.
Oh my God. Yes, by
She's
all means, bring that in on Thursday, Will.
okay. She loves to make food. She's retired and that's all she does. Every time I work for her for painting a barn and stuff, I gain 10 pounds.
Oh my God. But,
She makes
I have
homemade.
those the wipes there on the table, so if anybody's a little scared and they're wrapped in plastic, they can go ahead and wipe them real quick and still eat them. No.
Gotcha.
So yeah, definitely bring that in. That sounds like a good plan.
Okay. See ya.
All right, buddy.